So we're going to start. This is lesson 19. And we're talking about the Laplace transform. So this is a fundamental method in solving differential equations, both ordinary differential equations and partial differential equations. And we started to talk about this on Wednesday of last week. And we'll continue. So let's see, can you hear me? I don't have any response, but
Yeah.
Okay, fine. So, and also let me remind you that there's a makeup class on Friday at 11 where I'm just going to be going over homework problems and any other problems, but I want to cover sort of the theory today and Wednesday, and reserve Friday and maybe another extra session for going over homework problems. So if we have a function f of t, and the function has to satisfy some simple property that almost every function we deal with satisfies. It's piecewise continuous from 0 to infinity, and exponential growth at infinity. And what that means is that there exists some number, numbers m and c. So there exists m greater than 0 and c such that f of t in absolute value doesn't grow faster than e to the c times t. So you have exponent, so an upper bound for f of t, the absolute value of f of t, some constant times some exponential function. So almost every function we deal with has this property. Exponential functions do, trigonometric functions, polynomials, and so forth. And for such a function, the Laplace transform of the function f of t is, we write it in two different ways. Script L of f, it's going to be a function of s, or sometimes we write capital F of s. So these are just alternate notations for the same thing. The integral from 0 to infinity f of t e to the minus st dt. And so long as this condition is satisfied, the integral, this improper integral, converges. So this improper integral converges because of this exponential growth bound. And let me just review some of the properties of the Laplace transform that I proved on Wednesday of last week, and add a few more, and then give two examples of how we can use the Laplace transform to solve an ordinary differential equations and to take a partial differential equation in two variables and reduce it to an ordinary differential equation in one variable. And in the book of Logan, so this is the reference, section 2.6. So pages 106 to 116. Okay. So for example, suppose we take the function 1. Oops. Yeah. The function 1. Laplace transform of 1 is the integral from 0 to infinity of 1 e to the minus st dt. Again, let's just do it. We take the integral from 0 to b e to the minus st dt. Take the limit of that as b goes to infinity. That's the definition of the improper integral. What's the antiderivative of e to the minus st? It's minus 1 over s e to the minus st. So minus 1 over s e to the minus st evaluated from t equals 0 to t equal b. That's the limit as b goes to infinity of minus 1 over s e to the minus sb minus 1 over s, which is plus 1 over s at t equals 0. As b goes to infinity, this goes to 0, so we get 1 over s. So this is our first example of a Laplace transform. L of f of s is the integral from 0 to infinity, f of t e to the minus st dt. Laplace transform of 1 is 1 over s. Okay. Suppose we let capital F of s be the Laplace transform of f of t e to the minus st dt. That's the Laplace transform of f. Suppose I multiply f by e to the at. So I take e to the at times f. What's the Laplace transform of that? That's the integral from 0 to infinity, e to the at f of t, e to the minus st dt. And that's just the Laplace transform of this function. Of course, this is the same as the integral from 0 to infinity, f of t, e to the minus s minus at dt. Of course, e to the at times e to the minus st is e to the minus s plus a, or e to the minus the quantity s minus a dt. Suppose let's see. I'm trying to come up with a clever way to do something. Well, since I can't find a clever way to do what I wanted to do, I will do something else. Let's see. I want to just keep computing some of these Laplace transforms because it's very important. Oh, I should also, let me start by saying, first of all, well, let me do another calculation. Suppose I take the function f of t equals t. So the Laplace transform of t is the integral from 0 to infinity, t e to the minus st dt. We have to compute this integral. We can use integration by parts. T e to the minus st, derivative of t is 1, integral of e to the minus st is minus 1 over s e to the minus st. So this is going to be equal to t times this, minus 1 over s e to the minus st. St goes from 0 to infinity, minus the integral of in this direction, which is plus 1 over s, the integral e to the minus st dt from 0 to infinity. This is 0 plus 1 over s, the Laplace transform of 1, which is 1 over s. So we get 1 over s squared. So I claim that in general, the integral, the Laplace transform of any power of t which is going to be the integral from 0 to infinity, t to the n e to the minus st dt, is always equal to the following, n factorial over s to the n plus 1. And you will note that this is already, so proof. This is for all integers n greater than or equal to 0. So what is this for n equals 0? It says the integral, the Laplace transform of 1, 0 factorial is 1, 1 plus 0, 0 is 1 over s. We already proved that. And for n equal 1, this says the Laplace transform of t is 1 over s squared. I already proved that. So assume that it's true for some n integer, let's say n greater than or equal to 1. That is, we assume that the Laplace transform of t to the n is n factorial over s to the n plus 1. And we want to prove it. So what do we have to prove? The statement for n plus 1, which is that the Laplace transform of t to the n plus 1 is equal to n plus 1 factorial over s to the n plus 2, right? We're assuming this is true for some number n. I want to show it's true for the next integer, n plus 1. So this is what we have to prove. So what is the Laplace transform of t to the n plus 1? That's the integral from 0 to infinity, t to the n plus 1, e to the minus st dt. Let me do it very carefully. I'll do it exactly using the definition of the improper integral. The integral from b to infinity, the limit as b goes to infinity, the integral from 0 to b, t to the n plus 1, e to the minus st dt. We'll compute this integral by parts. We have t to the n plus 1 and e to the minus st. The derivative is n plus 1, t to the n. The antiderivative is minus 1 over s, e to the minus st. So using integration by parts, the integral from 0 to b, t to the n plus 1, e to the minus st dt. This is equal to minus 1 over s, t to the n plus 1, e to the minus st, evaluated from t equals 0 to t equal b, minus the integral of this times this. So I have minus times minus, that makes it plus 1 over s, n plus 1, t to the n, e to the minus st dt, from 0 to b. So the integral from 0 to b, t to the n plus 1, e to the minus st dt, is equal to this. Let's see, what is this? When t is equal to b, so I get minus 1 over s. When t is equal to b, I get t to the n plus 1 over e to the sb, minus what this is equal to when t is equal to 0, and this is 0 times 1 is 0, plus n plus 1 over s, the integral from 0 to b, t to the n, e to the minus st dt. So therefore, the Laplace transform of t to the n plus 1 is this improper integral. This is the limit as b goes to infinity of this. T to the n plus 1 minus over s, e to the sb, plus n plus 1 over s, integral from 0 to b, t to the n, e to the minus st dt. As b goes to infinity, this goes to 0. We get n plus 1 over s, the integral from 0 to infinity, t to the n, e to the minus st dt. This is the Laplace transform of t to the n. That's n factorial over s to the n plus 1. N factorial times n plus 1 is n plus 1 factorial over s to the n plus 2. Okay. So now we know the Laplace transform of every power of x. And we now know, I claim, the Laplace transform of every polynomial, because the Laplace transform is a linear operator. And what that means is for functions f of t and g of t, and constants c1 and c2, the Laplace transform of, or I'll just call them a and b, take the Laplace transform of a f of t plus b g of t, that's the integral from 0 to infinity, a f of t plus b g of t e to the minus std, This is A, the integral from 0 to infinity, f of t e to the minus st, plus b times the integral from 0 to infinity, g of t e to the minus st. That's A times the Laplace transform of f, plus b times the Laplace transform of g. So this means we now know the Laplace transform of any polynomial. If you take the function f of t to be, I don't know, 7t cubed minus 8t squared plus 3t plus 19, what is the Laplace transform of f of t? It's 7 times the Laplace transform of t cubed minus 8 times the Laplace transform of t squared plus 3 times the Laplace transform of t plus 19 times the Laplace transform of 1. The Laplace transform of t cubed is 3 factorial. Oops. To go back for a second. 3 factorial over s to the 4th. When I say I go back, it's because I just have to make sure I state things correctly. Laplace transform of t to the n is n factorial over s to the n plus 1. So this should have been, yeah, this is right, n factorial s to the n plus, yeah, no, I did everything correctly. That's good. So minus 8 times 2 factorial over s cubed plus 3 times 1 factorial over s squared plus 19 times 1 over s. 3 factorial is 6 times 7 is 42 over s to the 4th. 8 times 2 is 16 over s cubed. 3 over s squared, 19 over s. So for this polynomial, using the linearity of the Laplace transform, we get the Laplace transform of the polynomial. Okay. Any questions about this? What about the exponential function? What's the Laplace transform of e to the at? That's the integral from 0 to infinity, e to the at, e to the minus st dt. That's the integral from 0 to infinity, e to the minus s minus a t dt. That's the limit. B goes to infinity. Integral from 0 to b, e to the minus s minus at dt. What's the antiderivative of e to the minus s minus a t? It's minus 1 over s minus a e to the minus s minus at, evaluated from t equals 0 to b. That's the limit as b goes to infinity, minus 1 over s minus a e to the minus s minus a times b. Minus this when t is equal to 0. When t is equal to 0, this is 1. So you get minus plus 1 over s minus a. What is this? Now, If s minus a is positive, this goes to 0. But if s minus a is negative, this goes to infinity and the integral diverges. If s minus a is 0, this is 0. You get minus 1 over s minus a. So if s minus a is greater than 0, then, in other words, if a is less than s, then L of e to the at is 1 over s minus a for s bigger than a. So the Laplace transform of the exponential e to the at is only defined for s greater than a. That's what it's equal to. I'd like to try to compute the Laplace transform for the sine, and normally I would do this using complex numbers, but let me try to do it first without using complex numbers. Suppose I want to try to compute the Laplace transform of the sine of t. So that's the integral from 0 to infinity of sine of t e to the minus st dt. So this function is bounded by 1. This certainly converges. And this is the limit as b goes to infinity, integral from 0 to b sine t e to the minus st dt. So let me try and do this integral. So if I have sine t and e to the minus st, when I differentiate, I get cosine t and minus 1 over s e to the minus st. So the integral from 0 to b sine t e to the minus st dt is sine t minus 1 over s e to the minus st, evaluated from t equals 0 to b, minus the integral of this times this, minus times minus s is plus 1 over s cosine t e to the minus st dt from 0 to b. So I have to do this integral. So to do this integral, let me again try to use integration by parts. Cosine t e to the minus st. Derivative of the cosine is minus the sine. The antiderivative of e to the minus st is minus 1 over s e to the minus st. So the integral from 0 to b of cosine t e to the minus st dt is minus 1 over s cosine t e to the minus st evaluated from 0 to b, minus the integral of this times this, minus times minus is plus, so this is minus times plus, which is minus 1 over s, the integral of sine t e to the minus std from 0 to b. Okay. All right, well, all it is first year calculus, so we just keep going. So I take this expression for the integral of cosine times the exponential and plug it in here. So what I get is the integral from 0 to b sine t e to the minus st dt is equal to this. Let's see. When t is equal to 0, sine 0 is 0. So this is just minus 1 over s sine of b, I'm plugging in t equal b, over e to the sb plus 1 over s times this integral. But this integral is equal to this minus this. So that's minus 1 over s. When t is 0, cosine of 0 is 1, e to the 0 is 1. So minus 1 over s, 1 minus cosine b over e to the sb minus 1 over s times the same integral. So if this is 1 over s times 1 over s, it's 1 over s squared. If I bring this over to the other side, I get this integral from 0 to b sine t e to the minus st dt. And I have 1 over s plus 1 over s squared times this equals this times this. Minus 1 over s squared plus 1 over s squared cosine b over e to the sb. So somewhere in this, I know there's a little mistake, but I'll come back and work it out in a moment. So what happens as b goes to infinity? As b goes to infinity, sine b over e to the sb goes to 0. Cosine b over e to the sb goes to 0. It looks like we're left with just minus 1 over s squared. I would like that to be a plus, but let me just write down what this says then. It says that 1 plus 1 over s squared, which is the same as s squared plus 1 over s squared integral from 0 to infinity sine t e to the minus st dt equals minus 1 over s squared. I know there should be a plus. I'm going to come back in a moment and look at that. Equals 1 over s squared, which implies that the Laplace transform of the sine of t, that's this, is equal to 1 over s squared plus 1. Now, I just want to go back and see where I messed up getting that sign. So here we are. And let me do it slightly more generally also when I go through it again. Suppose instead of sine t, I want to look at sine of a times t, just slightly more general. So this is the integral from 0 to infinity of sine of at e to the minus st dt. So that's the limit of sine of at of this. Now, when I integrate by parts, if this is the sine of at, well, actually, Let me not do that because it's too hard squeezing in these letters. But just keep with sine t. So sine t cosine t, e to the minus st minus 1 over s e to the minus st. So this integral is the integral from 0 to b. This times this, sine t times this, blah, 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 that's correct. Minus the integral this way, which makes this plus 1 over s, integral of the cosine. And here, when t equals 0, I get 0. So this is really just sine b minus 1 over s sine b over e to the sb. That's perfectly correct. Plus 1 over s times this integral. Okay, now to do this integral, again, we're using integration by parts. Cosine, derivative of the cosine is minus the sine. E to the minus st, the integral is minus 1 over s e to the minus st. So the integral of cosine e to the minus st is minus 1 over s cosine t e to the minus st from 0 to b minus this integral. And when I evaluate this piece, when t is equal to b, I get where did I plug that in? Well, I think the next step, I just took this and I plugged it into this. So this integral is minus 1 over s sine b over e to the sb plus 1 over s times this integral when b is 0. No, sorry, when t is 0, I get 1. I get 1. So oh, right. Plus 1 over s. It's what I get when this is equal to b is right, so minus 1 over s. I just wrote this down backwards. So minus 1 over s. When t is equal to b, this is cosine b over e to the sb minus what I get when t is equal to 0, which is 1, which makes this minus 1 over s times minus 1 makes this a plus. That was the only mistake that was here. Okay, so believe it or not, that is the Laplace transform of the sine. And if we had the Laplace transform of the sine of a times t, this would be a squared over sine squared plus a squared. And if we needed to compute the Laplace transform of the cosine of at, we would get s squared over s squared plus a squared. Now, so we just calculated the Laplace transforms of some of the most basic elementary functions, polynomials, exponentials, sine and cosine. There's one more which we'll mention later, but okay. All right, this is calculus. What can you do with calculus? I mean, it's just calculus. Again, let me remind you of the linearity of the Laplace transform. If I take the Laplace transform of functions, a u of t plus b v of t, that's the Laplace transform of u times a plus b times the Laplace transform of v. Or if I use my alternate notation, the Laplace transform of a function little u is capital U of s. The Laplace transform of the function little v is capital V of s. So what about multiplicativity? If we take the Laplace transform of u and times the Laplace transform of v, is that the Laplace transform of the product? And the answer is no. Right. So it's not the case that the Laplace transform is multiplicative in the sense that the Laplace transform of the product of two functions is the product of their Laplace transforms. But there is a very beautiful relation that does describe the Laplace transform of two functions, and that is something called convolution. So if you have functions u of t and v of t, the convolution, right, u star v of t, is defined as follows. It's the integral from 0 to t, and then you can choose your favorite dummy variable. So the text uses, that is Logan's text, uses tau, u of t minus tau v of tau dt. So this is the definition of the convolution of two functions. And there's a beautiful theorem that says if u of s is the Laplace transform of u of t, and v of s is the Laplace transform of v of t, then the product of the Laplace transforms is the Laplace transform of the convolution of u and v. It's not the ordinary product of u times v, but it's the convolution product. And the proof, again, uses some calculus, maybe advanced calculus, but it's important to sketch the proof. Suppose I want to calculate the Laplace transform of u convolution v at s. This is the integral from 0 to infinity, u convolution v of t e to the minus st dt. This is the integral from 0 to infinity. What is this convolution? That's another integral, the integral from 0 to t, u of t minus tau v of tau d tau e to the minus st dt. So this is a double integral. And let's just draw a picture of the region where we're integrating over. Let's say this is t and this is tau. So t goes from 0 to infinity. And for each t, tau goes from 0 up to t. So for each t, when we integrate with respect to tau, we're integrating along these vertical lines. So we're integrating over this region. But so this region we can describe in two ways. So for 0 less than t less than infinity, tau is between 0 and t. Or alternatively, for tau between 0 and infinity. T, for every tau, t goes from tau to infinity. Now, if u and t are continuous functions with continuous partial derivative, continuous derivatives, and so forth, you can interchange the integrations. So the integral from 0 to infinity with respect to t, the integral from 0 to tau with respect to tau of whatever you're integrating is the same as the integral from 0 to infinity with respect to tau times the integral from tau to infinity with respect to t, that same thing you're integrating. That's the interchange. And what is it that we're integrating? That's the integral from 0 to infinity, integral from tau to infinity. U of t minus tau, v of tau, e to the minus st, dt, d tau. You'll notice this only depends on tau. Right, so I'm integrating with respect to t. This doesn't depend on t, this just depends on tau. So this is the integral from 0 to infinity. I can take this outside, v of tau, the integral from tau to infinity, u of t minus tau, e to the minus st dt, d tau. In this, if I change variables, suppose I let x equal t minus tau, this becomes the integral when t is equal to tau from 0 to infinity, u of x e to the minus s, x plus tau, dx, d tau, v of tau, integral from 0 to infinity. This is the integral from 0 to infinity, v of tau. This is e to the minus sx, e to the minus s tau, e to the minus s tau. I can take outside integral from 0 to infinity, u of x e to the minus sx dx, d tau. But this is just the Laplace transform of u at s. So this is equal to u of s times the integral from 0 to infinity, v of tau e to the minus s tau d tau. That's u of s, and this is the Laplace transform of v of s. So that is the proof of the convolution theorem. The Laplace transform of the convolution of two functions is the product of their convolutions. Okay. Let me just reprove the differentiation formula for the Laplace transform, which I showed last time, and then we can use it to solve. The whole purpose is to learn how to solve some differential equations. So suppose I have a function u, and I consider the Laplace transform of u prime, the derivative. That's the integral from 0 to infinity u prime of t e to the minus st dt. Let me do integration by parts. U prime e to the minus st. Antiderivative is u, derivative is minus s e to the minus st. So this is equal to u of t e to the minus st from 0 to infinity, minus the integral this way, which is minus times, which is plus the integral u of t e to the minus st dt from 0 to infinity. This is just the Laplace transform of u. When t equals 0, I get u of 0. At t goes to infinity, u of t over e to the t should go to 0. So this is minus u of 0. So this says that the Laplace transform of the derivative of a function is s times the Laplace transform of u minus u of 0. Suppose we take the second derivative. So this is the derivative of the derivative. So by replacing u with u prime here, we get s L of u prime minus u prime of 0. And now plugging in for L of u prime, this is s times this, we get s squared L of u minus s u of 0 minus u prime of 0. So if we know some initial conditions for u, namely u of 0 and u prime of 0, we can reduce the Laplace transforms of the derivatives to the Laplace transforms of u. So let me just write those two. So if capital U of S is the Laplace transform of the function U at S, then what we have is that the Laplace transform of U prime is S U of S minus S at 0. S U of S, this is just capital U is just the alternate notation for the Laplace transform. And L of U double prime is S squared U of S minus S times U at 0 minus U prime of 0. So now let's use the Laplace transform to solve an ordinary differential equation. So an example that is in the text is solve the initial value problem U double prime plus U equals 0 for t greater than 0, and we're given the initial conditions U of 0 equals 0, U prime of 0 equals 1. So according to this, the Laplace transform of U double prime plus U is the Laplace transform by linearity of U double prime plus the Laplace transform of U. Laplace transform of U double prime is S squared U of S minus S U of 0 minus U prime of 0 plus the Laplace transform of U, which is U of S. So this is equal to S squared plus 1 U of S. U of 0 is 0 and U prime of 0 is 1. S squared plus 1 U of S minus 1, and that's equal to U double prime plus U, the Laplace transform of 0, which is 0. So this is equal to 0. So what do we know? We know that our unknown function U has a Laplace transform equal to 1 over S squared plus 1. What is the function whose Laplace transform is S squared plus 1? Well, this is sort of the inverse problem. Up to now, we've given a function, we try to calculate the Laplace transform. Now we know the Laplace transform is 1 over S squared plus 1. That means that the function is sine of t. Because that was the calculation we did half an hour ago. We computed the Laplace transform of the sine of t, and it's 1 over S squared plus 1. And functions, if two functions have the same Laplace transforms, they're equal. And you can check sine t does satisfy the differential equation and the initial condition. Let me make up another problem and see if we can solve it. So you want to solve y double prime plus y prime plus 2y equals 0 with the initial condition. Let's say the solution is u of 0 and u prime of 0, both equal to 1. So, or y of 0 and y prime of 0 equal 1. So, take the Laplace transform. So 0 is the Laplace transform of 0. That's the Laplace transform of y double prime plus y prime plus 2y. The Laplace transform of y double prime is s squared. I'm using capital Y now for the Laplace transform. Capital Y of s minus s times y of 0 minus y prime of 0 plus L of y prime. That's s y of s minus y of 0 plus 2 Laplace transform of y of s. So that's s squared plus s plus 2 times y of s. And y of 0 and y prime of 0 are both 1. So this is minus s minus 1 minus 2. So that means y of s is equal to s plus 2 over s squared plus s plus 2. Then just double check. Y of s minus sy of 0 minus y prime. So minus 1 minus 1 minus 1. Well, looks okay. So what this says is that the unknown function y, the solution of this differential equation, has a Laplace transform which is equal to this. Let's see. Just to make it a little bit, I suppose I made this a 3. Let's see what happens. 3. Then this is a 3. I just want this to be able to factor. 3s minus 4. So if I just, this is my differential equation, y double prime plus 3y prime plus 2y equals 0. You take the Laplace transform, you get 0 is the Laplace transform of y double prime, 3 times the Laplace transform of y prime, 2 times the Laplace transform of y. So this is s squared y minus s minus y prime. 3 times this, 2 times this. So what am I? So I have s squared (3s) plus 2y of s. And I have minus s minus 1 minus 3 minus 4. So this is just equal to this. s plus 4 over, and this factors s plus 1 times s plus 2. And the easiest thing to do, if you remember calculus, is try to write this as partial fractions. So to do that, that means that s plus 4 is a times s plus 2 plus b times s plus 1. If you let s equal to minus 1, you get 3 equals a. And if you let s equal to minus 2, you get, this is minus b equals minus 2. So y of s is equal to 3 over s plus 1 minus 2 over s minus 2. We worked out the Laplace transform of things like s plus 1. And right, so let me just recall. The Laplace transform of e to the at is equal to 1 over s minus a. So this is equal to 3 times the Laplace transform s plus 1, a of e to the minus t, minus 2 times the Laplace transform of e to the minus 2t. So my solution, y of s, is equal to 3 e to the minus s minus 2 e to the minus 2s. Or if you want the variable to be t, you just change it to t. That's fine. That's the solution. So this is using the Laplace transform to solve an ordinary differential equation. Of course, our goal is to solve partial differential equations. So we just have to step it up a little bit, not very much, because now we're looking at functions of two variables, say u of x and t. And the Laplace transform of u of x and t, which will be a function of s, x and s, again, this is defined as usual, the integral from 0 to infinity, u of xt e to the minus st dt. So x is a parameter, and this gives us some function of s and t. Suppose I take the Laplace transform of the partial of u with respect to t. That's the integral from 0 to infinity, partial of u with respect to t, e to the minus st dt. Well, that's just our formula before for the Laplace transform of the derivative. That's s times u of xs minus the value at 0, t equals 0. And if we take the second derivative of u with respect to t, we get s squared u of xs minus s u of x0. It's supposed to be a 0 here. Minus u sub t of x0. And if we take the partial with respect to x, that's even easier. So that's just the integral from 0 to infinity, u sub x of xt e to the minus st dt. Just take the derivative outside, you get u sub x of xs. So these are all theorems, and maybe I'll prove them on Wednesday, but it really is exactly the same proof as in the one variable case. And what I want to show in the last couple of minutes is how you can use the Laplace transform to reduce a partial differential equation to an ordinary differential equation. So the example, which is in Logan's text, if I can find it. It's like a heat equation or a diffusion equation. It's the same heat, it's the same equation. U sub t minus uxx equals 0 for x greater than 0, t greater than 0. And we have the initial condition that at time 0, u of x0 is equal to 0. This is for x greater than 0. And the boundary condition is that the left-hand boundary, that's equal to 1 for all t greater than 0. So what we get is 0 is the Laplace transform of 0, is the Laplace transform of u sub t minus u sub xx. That's the Laplace transform of ut minus the Laplace transform of uxx. The Laplace transform of u sub t is s times the Laplace transform of u minus u at x0 minus, now Lux is ux, L of the second derivative is just the second derivative. So this is let me use my notation capital U because it's better. This is SU of XS minus the second derivative of U equals 0. This is, well, I need more time, so I'm going to explain this on Wednesday. But we start with this partial differential equation. And when we take Laplace transforms, this is an ordinary differential equation in the function u as a function of x. So this is an ordinary differential equation for u with respect to x. This is a very simple differential equation. This is just the differential equation, sy minus y double prime equals 0, y double prime equals sy. So this just has the solution e to the square root of st and e to the minus square root of st. Okay? This is a differential equation. It's an ordinary differential equation. We're only differentiating with respect to x. All right, well, maybe this was a little bit more complicated than I thought. So what I urge you to do is to really study this section of Logan on the application of the Laplace transform. As I said last week, in partial differential equations, we have 3 methods so far. And I guess I should put together a better, a longer homework assignment with these. So we have separation of variables, which leads to Fourier series in most cases that we're going to look at. For first order partial differential equations, we had the method of characteristics. And now for certain partial differential equations, we have the method of Laplace transforms. Laplace transform reduces the PDE to an ODE, but then we spent a month or two studying ordinary differential equations. So once we get the ordinary differential equation, we know how to solve it. Okay. Questions about this? It's only a few pages in the books. There's also a few pages in the Farlow book on Laplace transform. But there is a lot to think about. And if you've not seen a Laplace transform before, and there's no reason why you should have, you should spend a little bit of time just computing the Laplace transforms of elementary functions, because it's a skill that it's important to acquire. Okay. All right, so this week we have class on Wednesday and then again on Friday. And I'll be back here Wednesday morning. Okay. All right. Take care, everybody.